And generally, they start it like this. Okay, so you're not starting that model from the ground up with the birth rate and death rate given to you. Okay, but just say rate of change of population, Kp times 200 minus P. Okay, where P of T is the population in millions, T years after 1940. Okay, so what does number 88 ask of us? I didn't get my book out.
88 or?
Oh, sorry, number 21 on page 88.
The country's population for the year 2000 growing at a rate of 1 million per year starting at
So it gives you some initial conditions. Number 21, suppose that the population satisfies that differential equation with K as a constant. Its population in 1940 was 100 million. So we got this. And if T tracks years after 1940, then 1940 corresponds to 0. T equals 0. Population in 1940 was 100 million. And it also said, and was then growing at a rate of 1 million per year. That's a statement about the growth rate. So, oops, that should be a T. So the growth rate of the population at that instant, when T equals 0, and I'm going to put population is 100 million, that growth rate is 1 million per year? No. It was then rated at 1 million per year, so it's 1 per year, 1 million per year. So that's a statement about the growth rate. We write that down like a related rate problem. Okay? The question that it asked us, predict the country's population for the year 2000, which is 60 years. So in the year 2000, this is T equals what? 60. Right. So what we want, it's always a good idea. In related rates problem in Calc 1, and some of those problems in Calc 2, I just remind myself at the beginning what I want, what I'm given. Okay? So keep my eye on what I'm after. We want to know the population in the year 2000. Okay? So that's our goal. All right, so we have to solve this equation. Yeah? Well, it is separable. That's the good news. Chapter 2, we're not doing any of that stuff right now. Well, not with this problem. I'm going to separate this as follows. dp over, and I got to get this whole expression with p. p 200 minus p, right? Equals k dt. Okay, we're good with that? Now I got to integrate. And the problem is this integration on the left is a little tricky. Okay, and what we're going to use is a little technique. P times 200 minus P equals, now this, we could, hopefully this expression is the result of adding two simpler expressions, one with the denominator P, and the other with the denominator 200 minus P. Okay, everybody know what this technique is called? I want to find A and B. Yes. Partial fractions.
You can show me that.
Yeah, we want to find A and B that make that happen. Okay? So this is a little bit of side work. All right, so if I multiply both sides of this equation by that denominator, P 200 minus P, I'm going to get 1 on the left equals what? When I multiply, imagine, I'm not going to write it.
A 200 minus P.
Yeah, when I multiply P times 200 minus P, everything's going to cancel on the left. I get 1, that numerator. On the right, the P's are going to cancel out. I'm going to have A times 200 minus P plus, and the 200 minus P is going to cancel with the 200 minus P, and I'm going to have B t. Okay? So let's keep our eye on the prize. What are we after? We want to find a and b that makes this true. All right, now what I'm going to do is I got 200a minus ap. Okay.
T equals, no, so T equals
Says
0.
P equals
Mhm.
0.
And then you'll get A.
Oh, okay.
Divide by 200.
Oh, that's how you can do it in one of two ways. If you set p equals 0, you can solve for a. Is that right?
That's right.
Okay. A couple ways you can do this.
What's the other way?
Oh, just equate. Well, maybe we'll talk about it in a second. But I'm going to go with that idea. If p is 0, then that's gone, and I get 200a equals 1.
Can we really do that if there's also a relationship where p equals 0 makes it undefined?
Right, that will be a 0 population. It would make this down here undefined, but it wouldn't make the original differential equation undefined. It would say dp dt equals 0 constantly. Yeah. Should we do it this way? I already wrote it in the pen, didn't I?
It doesn't work, it doesn't work this way?
It does. It does. So if I solve this, it's not that bad. 1 over 200. Okay? And with p equaling 200, that's gone. You get 200b equals 1, right? Yeah, I think this way is quite simpler. And you get b equals 1 over 200, right? Okay, so there's our partial fraction. I found what a and b are. And what's 1 over 200? 0.01 or something like that? 1 200. Yeah, it's fine.
5, yeah.
Oh, right. 1/2 of 100. 0, 0, 5. Okay. The other way to do it, might as well, I'll show you. From there, and I'm going to write this on this side of the equation, a times 200 minus p plus b times p equals 1. If I multiply this out and collect like terms, p is a variable, a and b are constants we're looking for. I have 200a, I got minus ap plus bp, or plus bp minus ap, right? 200a plus, and I factor out the p, and it would be b minus a, p equals 1. Now, on the right-hand side, we have a constant. On the left-hand side, we have a polynomial in p. You equate like coefficients, or equate coefficients of corresponding terms. All right, so the idea being that this is the same as 1 plus 0p. There is no variable over here, so b minus a has to equal 0, right? And so b minus a has to match that 0, and that must be the 1. 200a equals 1. So in this case, you just get 200a equals 1. You get a system of equation, two unknowns, but this is the same equation you got. So this says a equals 1 over 200, right, same thing. And a equals b, this equation says that a has to equal b, so they're both 200. 1 over 200. So partial fractions, this is not a terrible case of it. Okay. All right. So, after that little aside, we got, and, oh, by the way, let's write this out. So it would be 1 over 200 over p plus 1 over 200 over 200 minus p, right? Now what I'm going to do, though, is pull out that 1 over 200 out front. So pull out that constant, 1 over 200 that we just found. This is dp equals, and what's the integral on the right side? Let's just leave it here. We'll leave it with the same step. K dt. Okay. All right. So next step, now I can integrate both of those, right? So what do we get?
LNP.
Natural log P. Now, I'm gonna disregard the absolute value. Why?
Population has to be positive.
Population, yeah, P represents population. We can safely assume that it's not negative at least. Okay.
Yeah.
Till there's, yeah. Negative people. No. All right, whatever this is. Now, I'm also gonna multiply both sides by 200, so we're gonna get rid of that constant anyway and multiply it over on this side. And then over here, what do I got? What's the integral of this term? Natural log 200 minus P, except that minus is in the back, so the chain rule would apply, and this would be a negative 1 out here. So we have to have a negative to counterbalance that. Right? Have a negative, and then if you find the derivative of this, it's 1 over 200 minus P times negative 1. It's going to knock that out and make it plus again. Okay? Equals, what do we got on the right side?
200 KT.
All right, yeah, we multiply both sides by 200, so I'm going to have 200 KT. K, we're integrating with respect to T, so I don't get K squared over 2. This is constant with respect to T, so I just pick up the linear term, okay, plus some arbitrary constant there. Yeah? Okay. So after that step, oh, here's the good thing. It's the difference of natural logs.
What's the dividing here?
Oh yeah, that little, yeah. Natural log of A minus natural log of B is the same thing as natural log of A over B. So it puts this term back instead. And I'm going to put that in absolute value, or at least the bottom, because we don't know if the population is more than 200 million or less than 2. Well, we do when we use the initial condition. All right. Equals 200 KT plus C. All right, good. Now I'm going to exponentiate each side. I think that's the right term to use. E to the natural log of all that is just all that, right? So we get P over 200 minus P. And the absolute values, right? If this expression is positive, 200 minus P, then the absolute values are redundant, okay? We do know from the beginning, though, that the initial population at time 0 is only 100. So it's 200 minus 100. It starts off, this would be positive. All right. And over here, we get, if I raise both sides, oops, sorry, after raising this to e to that power, I'm going to get e to the 200 kt times e to the c, which I'm going to pull out and just call a. Okay, I also assume that 200 minus p is greater than 0, which is reasonable because the population starts off at 100, so the absolute value of 200 minus p would just be 200 minus p. Positive, okay? All right, now I can multiply both sides by the 200 minus p in the denominator, and I'll have 200 minus p a e to the 200 kt, right? Distributing this, the ae to the 200 kt to both terms and adding that to the right side, or sorry, adding pa e to the 200 kt to the other side, to both sides, I'll have this. Okay, and over here I'm going to have just 200 a e to the 200 kt. Okay? Okay, good. This one is solvable for p, because once I get, so imagine distributing that, I'd have a minus pa e to the 200 kt. I added that to the other side to make it positive. Good thing is, these terms both involve p. Let's factor that. And finally, let's see, we got, divide both sides by the 1 plus a e to the kt, we get p equals, that's going to be down in the denominator, e to the 200 kt, and up here we got 200 a e to the kt. We're so close. Then it's just cleaning up. If I divide numerator and denominator by just by the e to the kt term,
Shouldn't the top be 200, e to the 200 KT?
Yeah.
what's that? Oh, 200 right there. Okay, divide numerator and denominator by e to the 200 kt. You have 200a to cancel out there. And in the bottom, I'd have 1 over e to the 200 kt. That's going to be e to the negative 200 kt plus a. Okay. Or we can write it like this. I like to have that term first. We got 200a over a plus e to the negative 200 kt. Now, all right, we've done the work in isolating the p, solving for p, but we didn't answer the question because we got a giant constant here, and we don't know what k is. That's the constant that we began with, and that has to do with the growth rate, but it's not simple proportion. It's not proportional to the population like law of natural growth, but we still need to solve for those. So how can I do that?
We know k is t of 0.
Okay, so now we use initial conditions. Here's the good thing. We're going to use this work, this specific example, for the general case and see where it all comes from. And I'm going to give you what the solution of the general logistic is. So the first condition is that we know that population at 0, which remember refers to the year 1940 actually, 40. So at that initial time, we had 100 million people. So putting in 0 for t here, what do we get?
0.
E to the 0, careful.
1.
That's 1. I'd have 200a over a plus 1 equals 100. Okay? Now that's an equation that you could solve in your calculator. That's fine. It's just a piece of this larger problem. Okay? 100 times 1 plus a. Yeah, if I multiply both sides by a plus 1, we get 100. A plus 1 equals 200a. That gives me 100a plus 100. 100a. So get that to the other side.
E equals 1.
All right. If a is 1, we get 200 equals 200, right? Distribute that out, subtract 100a from both sides, I get 100a equals 100. So a equals 1 in this case, yeah. All right. So there we go. Write down where we're at. A is 1. So A is 1, e to the negative 200 kt. Okay, we're getting there. Now we only have 1 unknown left. Okay? And this has something to do with the, proportionality, the growth rate. Okay, but we have another condition, right? What did that other condition say, though?
At t equals 0 is equal to 1.
Right, that other condition involved the growth rate. It said the growth rate at the initial year, 1940, when the population was 100 million people, the population was increasing at a rate of 1 million per year. Okay. So the other condition, I'm going to label these 1 and 2. The other condition says that the growth rate, when t, and I'm just labeling these just particular time and population, that growth rate was equal to 1. Okay? So keeping this on the same page, going back to our original differential equation, we know that at time 0, when the population was 100 million, I could put 100 million in there and dp dt equals 1. So dp dt equals 1, and we got k times p, which is 100 times 200 minus that 100. And that allows us to solve for k. This is the first time I think we've seen an initial condition that involves growth rate.
Sure.
Okay. But it does allow us to solve for k. K is going to be a very small number, I think. We got, that's 100, 100, 100 squared.
10,000.
Mm-hmm. 100 is 10 squared, yeah, that's 10 squared squared. 4 zeros. Mm-hmm. Oh, and this is what we call 1 times, I'm just going to do it in 10 to the negative 4. So yeah, that's a bunch of zeros and 1. 10 to 1 times 10 to the 1, 2, 3, 4. There we go. So k is very small there. All right, so that's our k value. So let's put that into the equation. Finally, p of t equals 200 over 1 plus e to the negative 200, oh wow, negative 200 kt. K is 10 to the negative 4. Mm-hmm. All right, oh, times 10 to the negative 4th. Let's just use our scientific notation. Wait, 1, 2, 3, it's going to be negative 0.02. Boom. Okay. So after a lot of work, we do have an explicit formula for the population in terms of time. Okay? All right. And it's not a pure exponential. See this exponential term in the bottom? Okay? This is kind of interesting. Well, let's first solve the problem that we're after. What were we after? Luckily I wrote down what we want. We want the year 2 population and predicted population in the year 2000.
See if the model's right.
T equals 60, right? And population and year 60 is 200, 1 plus e to the negative 0.02 times 60. And I just took the liberty of doing that. Roughly 0.70704 or something like that million.
So about half what it actually was.
300 million, yeah, like
Right.
2 years ago.
Right. Okay.
Maybe it's in the United States.
Oh yeah. It doesn't say. It doesn't. What does it say? It say just a country. Population of a country satisfies that differential equation. Yeah. Yeah. U.S. population and most countries' population are far more complex than what we have. We're assuming a constant death rate and just a linear birth rate with respect to the population. It's pretty simple. So imagine how much harder it becomes if you take all those other variables into account. Okay. So that's what they do with this, census. They try and build population models and predict things. Yeah.
I might be wrong, but it seems like we accidentally dropped an exponent off the top. So right before we found A. It seems like it's supposed to be 200 e to the
Negative 200 kt. Yeah, I put the 200 right here, and then times the k. K was 10 to the negative 4th, so yeah, I did multiply those.
Well, I think that was supposed to be one on top of
Over here? Over here? In this step? Like one that was here and then it gets dropped?
Okay, maybe I'm wrong. Never mind.
see it, but. Okay. So, no worries. All right, so it predicts a population of 153.7 million in 2000. All right. What I'd like to show you, finally,
Did you get Java installed? Or no?
they blocked Java because it's dead, and this thing's a Java-based applet.
Carly was trying to get Java working yesterday for the tools.
Yeah, it was working last year, so when they upgrade the computers, that's all of a sudden obsolete. They don't have all their settings to not allow Java, and they're like, that's a problem with them. Write them and tell them to rewrite all that code. Rice University. I'm gonna email Rice University and tell them they're obsolete. All right. So what I want to show you is we got a population model. This guy right here allows you to put in a first order differential equation, and the power of this thing is that I can call it P. I can keep that name, and our original equation was K times KP 200 minus P. Watch this. K P times 200 minus P. Now, close parentheses, it's yelling at me. It doesn't recognize that function or variable KP. I'm going to put a times in there between variable expressions. It doesn't recognize K. The independent variable is T, time, although this differential equation does not involve T. Okay, we'll define that in a second. That's called an autonomous equation. It does not involve the independent variable. But look at these parameter declarations. I need to declare that K is a parameter. We found it to be 0.0001, 10 to the negative 4. All right, so display window. Why isn't it asking me? Okay, this is T. It should recognize the independent variable T and give you the, anyway. So say time goes from, well, 0 corresponds to 1940. So 2000 is 60. Let's go to 65. And the P represents the population. We know that at time 0 there was, what, 100 million? 100. So let's go up to, I don't know, 175 million or something up there. And then hit get phase plane, or graph phase plane. Okay, it gives us something like that. At year 0 corresponding to 1940, there's 100 million. So that's our curve.
Oh, wow. Cool.
So I put in that initial condition just by clicking on it. We can check it out in the year, in 2000, that's year 60. See how close I was. Look at that, 150 and some change probably. Only it's hard to tell from the scale, isn't it?
Oh, it tells you on the bottom left. That's the readout.
Right, yeah, so I put the initial condition right there, and at year 60, somewhere between 140 and 160, but more than halfway in between, so maybe a tad over 150. So that graphs the solution curve. This is, it creates the phase, or the direction field, and then you can put in any initial condition if you want. Okay, so that's what the curve would look like. That's what it gives you. So, all right. Keep that open. I'm not going to mess with it. So that was that problem in a bottle. Now, they would assume that once you get to that point, you would use the general solution to the logistic model, okay, which we'll talk about in a moment. Now, what I want to do is talk about the population model we did day 2, which you may not remember. Day 2. Let's see if I still have that OG.